Okay, so I want to take a look at the third worksheet now, which is, the other ones are pretty simple. This one's a little bit more extensive. You're going to have to spend a little bit more time with it. But let's go through some of it together. I do have this little bit of the reference table photocopied onto the last page here. But it's always helpful to have a copy of the reference table handy. This picture here, hopefully you recognize this as the photoelectric effect. Shining the light onto this plate. I have a battery, I have an ammeter, and the electrons are flowing away from the negative side towards the positive side. So the name of this experiment, photoelectric effect. The significance of this, what does the photoelectric effect prove? Right? Well, because we can measure the current here, we can determine that the electrons always have specific amounts of energy. So therefore the light must have specific amounts of energy. Therefore light must be particles. How does this experiment relate to the following equation? E is equal to HF. What happens to the energy of the electrons when we change the frequency of the light? So you can think about that, answer that yourself. Energy of a photon, E equals HF. We have these questions here. An electron has an energy of 2.3 eV. What is the energy in joules? Do you guys remember that? How do we convert from an energy of 2.3 to joules? Well, we want to multiply this by 1.6 times 10 to the negative 19th. So 2.3 times 1.6 times 10 to the negative 19th comes out to be 3.68 times 10 to the 19th joules. That's how we do that. What is the energy in electron volts of an electron with a velocity of 6.2 million meters per second? So maybe I should get a separate sheet of paper for this, since there's not a lot of room here. So for number 2, how am I going to figure out how much energy is in the electron when what we're given is velocity? .2 million meters per second times 10 to the 6 meters per second. Well, we do have an energy. We do have a formula that relates velocity and mass. It's this: KE is equal to 1/2 mv squared. So in order to do this, we have to know the mass of an electron. So the mass of an electron comes from this sheet here. Rest mass of the electron, 9.11 times 10 to the negative 31. 9.11 times 10 to the negative 31 kilograms. So I want to know what the energy is. So this energy is going to be 1/2 times 9.11 times 10 to the negative 31 kilograms times the velocity squared, 6.2 times 10 to the 6th meters per second, and I have to square that. So 0.5 times 9.11 times 10 to the negative 31 times 6.2 times 10 to the 6th squared equals, so I get 1.75 times 10 to the negative 17th joules. But it wants this answer to be in electron volts. So I'm going to divide this by 1.6 times 10 to the negative 19th. So I take my answer divided by 1.6 times 10 to the negative 19th equals 109.4. 109.4 EV. That's how much energy I have. Going back to the sheet, what is the velocity of the electron with 3.2 electron volts of energy in number 1? So I'm going to set it up. I want you guys to do this one yourself, but I'm going to use this formula again. And for the kinetic energy, I'm going to put in this number here, 3.6 times 10 to the negative 19th joules. I still have the 1/2, and then you're going to put the mass in yourself. It's the mass of an electron again, 9.11 times 10 to the negative 31 kilograms, and you're going to solve that for V squared. All right, 4, what is the energy in joules and EV of a photon produced by a laser with 650 nanometer wavelength? So I need an energy, I'm looking for the energy. I need a formula that relates energy to wavelength. So I have E is equal to HF, and then we have the other version of it, which is HC over lambda. So that's how you're going to do number 4. Number 5, in X-ray with this wavelength. Oh, by the way, nanometers. So let's going back to 4 again. So my wavelength, 650 nanometers. So to convert that into meters, that's 650 times 10 to the negative 9th meters for the wavelength. Number 5, an X-ray with a wavelength of 0.02 times 10 to the negative 9th meters is absorbed by a material and releases an electron. Calculate the energy in joules and EV of the electron. X-ray with this, calculate the energy and EV of the electron. So how are we going to do this one? We're going to again say E is equal to HC over lambda. So when we do this, we're going to put this wavelength into here. Planck's constant, right? H is 6.6 times 10 to the negative 34. And the speed of light is 3 times 10 to the 8th. Yeah, so I think I'm just thinking about the different energy levels in the Bohr atom, but it's not telling us what the substance is. So this is the best we can do is assume that it all goes into the electron. So that's how I want you to do that one. Number 6, we have this diagram here. I have an incident photon that is colliding with an electron. The electron then gains energy, and the scattered photon then loses energy here. What is this called? What did we call this when it collides like this? It has the word scattered in it. Compton scattering is what this is called. What's the significance of this phenomenon? So what two things are conserved. What two things are conserved in this diagram here, in this situation? So you can go back and look at the PowerPoint if you don't remember. And how does this phenomenon relate to the following equation? P is equal to HF over C, or H over wavelength. We don't have this formula. We don't have this formula anymore. So real quickly, this is telling us that momentum is equal to Planck's constant times the frequency over c, or momentum is equal to Planck's constant over the speed of light. So let's just answer this one here. How does this phenomenon relate to the following equation? We're going to say that the wavelength is proportional to the momentum. So the wavelength, lambda is directly proportional to the momentum p. So the momentum of a photon is equal to Planck's constant divided by the photon's wavelength. Actually, this is, I wrote this. This is lambda. So it's actually, the wavelength is proportional to the momentum, but this is in the denominator. So how do we want to say that? So I'll say 1 over wavelength. So the inverse of wavelength is proportional to the momentum. Momentum of photon is Planck's constant divided by the photon wavelength. As an X-ray strikes a material and collides with an electron and is scattered, how does the wavelength of the scattered X-ray compare to the wavelength of the incoming X-ray? Well, let's see. Here I have higher energy, and then it hits the electron. This guy gains Ke, so he gains energy. This guy here loses energy, so he has less energy. If he has less energy, his frequency is lower, and his wavelength must be greater. And you can kind of see it in the picture, right? These waves are a little smaller, and these waves are a little bit larger here. Multiple choice. The energy levels of an atom changes as it absorbs and emits energy. Which of the following is not possible energy level of an atom? Now remember that energy levels always have to be specific orbits, so it can't be the 3/4. Explain why, and it's just because of the different energy levels. You can explain it more than that, but the electron only exists at specific orbits, at specific energy levels. A photon has a frequency of 1.14 times 10 to the 15th hertz. What is the energy of the photon? You can work that out yourself, but you're going to use this formula, and you're going to put this in for the frequency. Thinking critically. The helium neon laser emits photons with this wavelength. 632.8 times 10 to the negative 9th meters. Find the energy in joules of each photon emitted by the laser. E equals HF is how you're going to do that. A typical small laser has a power of 0.5 megawatts. How many photons are emitted each second by the laser? So we know that this power is 0.5 times 10 to the 3rd watts. And they're telling us that this is equal to an energy, or this power is equal to energy per time. And they're saying that that's equal to 5 times 10 to the negative 4th joules per second. How many photons are emitted each second by the laser? Well, one photon, we would use E is equal to HF, or this case, let's see, how many, a typical small laser has this many watts. How many photons are emitted? Oh, well, you have to use this. You can't solve unless you have to use that again. So you're going to use E is equal to HC over lambda. And for lambda, you're going to put in your 632.8 times 10 to the negative 9th meters. C is going to be 3 times 10 to the 8th meters per second. H is going to be 6.6 times 10 to the negative 34. So we're going to solve that for E, and then we're going to compare this number to this number here. So that's kind of a tricky one. Maybe we'll do that one together to make the video kind of long, but let's give it a shot here. So this is 70B. Actually, let's keep this sheet out. So, actually, we don't need that sheet. I've got it right here. So we're going to say E is equal to H 6.6 times 10 to the negative 34 times 3 times 10 to the 8th divided by 632.8 times 10 to the negative 9th. 6.6 times 10 to the negative 34th times 3 times 10 to the 8th divided by 632.8 times 10 to the negative 9th equals 3.13 times 10 to the negative 19th joules. So this is the energy of one photon. And this was telling us that it had a power rating of 5 times 10 to the negative 4th joules every second. And this is how much one of them is going to be. So how many photons are emitted each second? So I'm just going to take this and divide it by this. So the number we just got, and 3.13 times 10 to the negative 19th. So I get this, the number is going to be this crazy thing. Let's see, let's try this again. So I have 5 times 10 to the negative 4th is my total power. So I'm going to divide that by 3.13 times 10 to the negative 19th. So let's try that again. 5 times 10 to the negative 4th divided by 3.13 times 10 to the negative 19th equals, yeah, so I'm going to get 1.6 times 10 to the 15th electrons every second. All right, well, we did that one together, so you can just follow my math there. It was a little bit involved. And then on to the last page. In 1905, Albert Einstein concluded that the mass of a body is a measure of its energy content. we can write this in the more familiar form. This is probably the most famous formula in physics, E equals mc squared. Energy is mass times the speed of light squared. How much energy is produced when 2.5 kilograms of matter are completely converted into energy? E equals mc squared. So it's the mass, 2.5 kilograms, times the speed of light, 3 times 10 to the 8th meters per second, and that has to be squared. And I'm going to leave that for you to finish. Pretty simple. And that's it. This is just reference material down here. So please complete this worksheet, the ones we went over in this video and the ones I left blank as well, and submit that to the portal before Tuesday night. Thank you.